Hello, welcome back once again. Today we have this interesting improper integral. The integral from 0 to infinity, the arctangent of x divided by x multiplied by x squared plus 1 dx. So let's see how we're going to evaluate this nice looking integral involving the arctangent function. Okay, let us use the Fermat's technique. So here, let us define the following function. I of a is going to be equal to the integral from 0 to infinity. The arctangent of ax, then divided by x into brackets x squared plus 1 and then dx. Okay, that's cool. So we're going to differentiate with respect to a. At the left hand side, we're going to have the I prime of a, which is going to be equal to the partial derivative with respect to a of integral from 0 to infinity, the arctangent of ax divided by x into bracket x squared plus 1 dx. So this is equal to the integral from 0 to infinity. Here we're going to have the partial derivative with respect to a of the arctangent of ax, then divided by x into bracket x squared plus 1, and right over here is our dx. Okay, the derivative of the arctangent of ax with respect to a is very easy enough, right? If you use the what are we going to use? I think we're going to use the chain rule, right? So we call it the chain rule. So here, I prime of a is going to be equal to the integral from 0 to infinity. So up there, we're going to have x, right? Then divided by 1 plus ax squared, right? So here we're going to have this as divided by, remember we have x into bracket x squared plus 1, and then here we're going to have 1 plus a squared x squared, and then dx, of which you can see that the two x get cancelled from upstairs and downstairs, and here we have the integral from 0 to infinity of 1 divided by, so we have x squared plus 1 into bracket 1 plus a squared x squared, and then dx. So this is indeed the time we need the partial fraction decomposition. Okay, so are we going to do that here? I think I'm going to do it so that everyone will see how this can partially be decomposed, okay? Decompose, I mean. So let us partially decompose this fraction into sum of two fractions, okay? So let's do that. So let's say we're going to use another color from this side. So what are we going to use today? Let's use the red color. So say we have, remember what we have there, 1 all over, right, x squared plus 1 and 1 plus a squared x squared. Oh my god, this is going to be cool. Okay, well, without a partial fraction, I think we need to do something very cool. Okay, guys, just look at what I'm going to do. I think it's going to be very nice. So we're going to factor out the a squared from the denominator. So we're going to have I prime of a is going to be equal to the integral from 0 to infinity. So 1 all over, if you factor out the a squared, so we're going to have, remember we have x squared plus 1. And here we're going to have x squared plus 1 all over a squared. I don't know if you get the magic. Okay, so this is going to be equal to 1 by a squared, the integral from 0 to infinity. So we have 1 all over. So this is x squared plus 1. And this is x squared plus 1 over a squared. And here we have our dx. Now we can easily decompose this into sums of partial fraction. Okay, first, let us find out the difference between the products. Okay, so this is what I mean. If you check out, okay, so if you check out x squared plus 1 minus, remember at the numerator we have 1, so we need to make out 1 from here. Let's say 1 will be equal to, now let's check out. So this is going to be x squared, oh yeah, plus 1 over a squared. Then if you check this difference, if you check the difference, this is going to give us 1 minus 1 over a squared. But this is not equal to 1. Then we need to as well divide by 1 minus 1 over a squared. I don't know if you get the idea or if you get the magic. So here I prime of a is going to be equal to, so this is 1 over a squared, the integral from 0 to infinity. So up here we're going to replace the 1 at the numerator using the following. Remember this is, don't forget we have to put 1 minus 1 over a squared here. So this is going to be 1 all over 1 minus 1 over a squared. Okay. Then multiply by the difference. Don't forget this is x squared plus 1, right? Minus x squared plus 1 over a squared. So you can see this whole expression, multiply them together, they will give you 1. Then divided by, don't forget, we have x squared plus 1 multiply by x squared plus 1 all over a squared. And here we have y dx. So here we have I prime of a is equal to, so take this one outside, okay? So this is going to be 1 over a squared multiplied by 1 all over 1 minus 1 over a squared. Then, now, if you split the denominator, we're going to get the integral from 0 to infinity. So we have here x squared plus 1 divided by x squared plus 1 and x squared plus 1 over a squared. You get the idea? And then minus, here we have x squared plus 1 over a squared divided by, we have x squared plus 1 and x squared plus 1 over a squared. And we have our dx. This is becoming crazy. Now there are some nice cancellations going on. This. So this is exactly our target, okay? So I prime of a, remember, this is 1 all over. Find the products here. If you use a squared to open the bracket, we're going to have a squared minus 1. Don't forget. Okay, so here we have the integral from 0 to infinity. We just have 1 all over x squared plus 1 over a squared dx minus the integral from 0 to infinity 1 all over x squared plus 1. And here we have our dx. Where is this leading us to? Okay, so here I prime of a is going to be equal to 1 over a squared minus 1 in brackets. So this is going to give us 1 all over 1 over a, the arctangent of xa, which is same as a multiplied by the inverse tangent of ax. Hope I'm getting this right. And then minus here, this is just the inverse tangent of x. So remember we're taking this limit from 0 to infinity. Okay, so from here, I prime of a is equal to, this is 1 over a squared minus 1. So here, the a arctangent of infinity, right? That is putting the upper limit first. No need for the lower limit because the tangent of 0 is 0, right? So let's just make use of the upper limit. So a, the inverse tangent of infinity minus the inverse tangent of infinity. So here I prime of a is equal to 1 over a squared minus 1. So it is giving us or you need to factor out the pi over 2, right? So a multiplied by pi over 2 minus pi by 2. So this is same as 1 over a squared minus 1. So a into brackets, oh, is that a or pi by 2 in the brackets, okay? So there will be no space for this here. So let's go to the next line. So here, I prime of a is equal to 1 by a squared minus 1, right? Multiply by here, we factor out the pi by 2, and we're left with a minus 1. So don't forget this here is difference of two squares, right? So here we get I prime of a is equal to, this is 1 by a plus 1, a minus 1, multiply by pi by 2, multiply by a minus 1. And we see this both get cancelled. And here we have pi by 2 multiply by 1 over a plus 1. Now we need to integrate both sides, right? So integrate both sides, and the right hand side with respect to a, and at the left hand side we now recover our I of a, which is going to be equal to pi by 2 the ln of a plus 1 with a plus c. Now let's go back to check I of 0. Take a look at this place. If a is equal to 0, then I of 0 will be 0, right? Because the arctangent of 0 is 0, so everything turns out to be 0. And don't forget that our target integral here is equal to I of 1. Don't forget that. So now, from here, let's a equals 0. We get 0 is equal to pi by 2 ln of 1 plus 0 is 1 plus c. This implies from here that c is equal to 0. Therefore, our target integral I of a is going to be equal to pi by 2 the ln of a plus 1. And finally, let a equals 1, we get the solution to the integral. That is saying that I of 1 is equal to the integral from 0 to infinity, the arctangent of x divided by x into bracket x squared plus 1 dx, that this is equal to pi by 2 the ln of 2. So this right over here is our solution. Thank you for watching. Please subscribe.